Alright guys, good afternoon everybody. Just let me know if you all can hear me, please. Alright, cool. All right, so in today's session, what I'm going to be looking at, at this section of the broad topics that CXC indicated that's going to come, right? Which is electrochemistry, right? That is the section here. All right, I saw somebody asked about non-metals. Hopefully next week we might get a chance to go through that. We'll see. So here's what you guys need to know when it comes to electrolysis. The first thing that you all need to know, you all need to make sure that you all have a definition for what electrolysis is, right? Now, electrolysis is the passage of an electric current through an electrolyte producing a chemical change, right? So make sure you have that in your back pocket to be able to answer this question, right? What is electrolysis, right? So electrolysis is the passage of an electric current through an electrolyte producing a chemical change, or we can say, right, the decomposition of an electrolyte because of the flow of a current, right? So any one of those definitions could work. Just make sure you have a proper definition for what electrolysis is. Now, if you want to perform electrolysis, right, you need to have a power source. You need to have a battery, right? So on top here, this part here is what we call a battery, right? Now, in order to perform electrolysis, you need to have two electrodes. Now, electrodes could simply be carbon rods or platinum rods, right? Or even copper electrodes. So electrodes that are connected, or electrode that is connected to the positive terminal, is called my anode, right? So this here is my positive terminal, right? The electrode that is connected to the negative terminal of the battery is called my cathode. Right? So your anode is a positive terminal, your cathode is your negative terminal. So you need to be aware of what that is, right? Now, what we put the electrodes into, that is called our electrolyte, right? So you need to know what that is. So my electrolyte could be, right? It can be an ionic solution. The easiest example I can give you is salt dissolved in water. So normal common salt in a kitchen, or sodium chloride, right? It's an electrolyte. So NaCl aqueous, that's an electrolyte. Or it can also be a molten ionic compound, right? That can be my electrolyte. So this is a typical diagram for electrolysis. Please make sure you know how to sketch a simple diagram like this, right? Now, inside your electrolyte, you have positive ions. So inside of my electrolyte, I have positive ions, right? And we also have negative ions. Now, these things have special names, guys. So negative ions and positive ions. So positive ions are called cation ions, right? And negative ions are called anions. So these are things you need to be familiar with. CSEC can ask you any of these things here. Now, because the anode is positive, so this terminal here is positive and this terminal here is negative. And within this electrolyte, you have positive electrodes, you have negative electrodes, right? So let's say you have positive here and you have some negative here. What's going to happen is that your positive ions or your cations, they're going to move towards here. They're going to drift towards your cathode, right? Your negative ions, or what we call anions, drift towards the anode. They're going to do this, right? So these are things you need to be familiar with when it comes to electrolysis, right? Now, when we are talking electrolysis, you all need to be able to predict what is going to happen when electrolysis takes place, right? So there are several that the syllabus require you guys to know, but you need to know what actually occurs during the electrolysis process. Now, this is an exam question I get. There are 3 factors that affect what is discharged, right, during electrolysis, right? That's what is discharge. Yeah. So the first factor that affects what is discharged is your position in something called your electrochemical series. So you all would have done the reactivity series, right? There's something called the electrochemical series, and it starts off the same way: potassium, sodium, and we keep going down like that. So that's our electrochemical series. So the position in your electrochemical series affects what is going to be discharged. The second factor that affects what is going to be discharged is your concentration of your ions in the electrolyte, right? So the more concentrated a particular ion is, right, the more likely that is going to be discharged. And the third factor that affects what is discharged is the type of electrode. We have 2 kinds of electrodes. We have active electrodes and inert electrodes. An inert electrode could be something like carbon, or what we call graphite, right? Or platinum is an inert electrode as well, right? Now, when it comes to active electrodes, you can have something like copper. Copper can be an active electrode and something happens to the copper in this particular instance, right? So there are basically 3 factors that affect what is being discharged during electrolysis. So you need to be familiar with this, guys. Now, I just spoke about what we call my electrochemical series here. This here is what we call my electrochemical series, right? Now remember, your position in the electrochemical series affects what is discharged during electrolysis. So this here, these are my cations. So like potassium, sodium, those are cations, right? Now what you need to remember is that the ones lower down, right? The ones lower down will be discharged first, right? So this is discharged first, right? So if you have a mixture containing, let's say, sodium and let's say lead, right? Lead is going to be discharged first and not sodium. So the one lower down in the electrochemical series is going to be discharged first, right? Now, we also need to be familiar with this series as well here, and that has to do with anions, right? So in this case here, we have chlorine, bromine, iodine, right? But I need to include 2 more for you guys. OH minus, right, is below the fluorine here, right? And also, there are 2 more that we can stick in here just to be familiar with. We have the nitrate and we have sulfate. So nitrate is going to be here, NO3 minus, and we also have sulfate present here. Now, in terms of what is going to be discharged first, this here is going to be discharged first. Right? So this is going to help us predict what is going to be discharged in an electrolysis process. Right? So I saw somebody asking me online, when we electrolyze sodium chloride, why we don't get sodium? Sodium is high up in electrochemical series and is highly unlikely that it is going to be discharged. Right? What is discharged instead is this. But I'm going to go through several of the types of electrolysis you all need to know to make sure you understand this. Right? Now, so let's look at this first electrolysis that your syllabus says you need to know. So what I'm going to be using is dilute sulfuric acid, right? And I'm going to use graphite electrodes. So my anode and my cathode, they are graphite, right? Now, before you can understand what is happening during electrolysis, right? So I always tell my students, I always like to draw the diagram. I don't like to guess to figure out what's happening. I need to draw the diagram. Now, when it comes to dilute sulfuric acid, the first thing we need to be aware of, what ions are present in dilute sulfuric acid, right? So in dilute sulfuric acid, we have, let's write the formula, right? So sulfuric acid is this, H2SO4, right? The ions that we're going to get from this will be H plus, right? That's one set of ions. We also have the sulfate ion, SO4 2 minus, right? But always remember, when something is in solution, you will always have water present, right? So that's H2O. From the water, there are two ions we can get here, H plus and OH minus. So this is how you're going to analyze electrolysis questions. First thing you have to do is to figure out what is actually present in this electrolyte. I am using dilute sulfuric acid. So from the H2SO4, I will have H plus ions and I will have sulfate ions present. But I also have water present because it's a solution. And what I'm going to get from the water molecules, I'm going to get H plus and OH minus ions. So in terms of cations, all I really have is H plus, right? But I have the option of sulfate ions being discharged or OH minus ions being discharged. So here's what you need to analyze now. You need to figure out at your anode, remember your anode is your positive electrode, right? This is my positive electrode. The ions that are going to migrate towards my positive electrode will be my sulfate and my OH minus. But which one is going to be discharged? I've seen students decide, well, it's sulfuric acid, so let's discharge sulfate. But if I go back to the electrochemical series, look at where sulfate is and look at where OH is. OH is lower down in this electrochemical series. So therefore, what's going to happen is that OH is going to be discharged, right? Now, CXC gives you lots of marks for writing what we call the half equations for what is happening at electrodes. So it's this. You all need to learn of this equation. 4OH minus aqueous, right, produces 2H2O liquid, right, plus O2 gas, right, plus 4 electrons, right? You all need to learn this equation. So make sure, if you have not done so as yet, right, it's 4OH minus produces 2H2O plus O2 plus 4 electrons. You need to learn of this equation, right? Because you're going to see it a lot. So learn this, please, right? So that's what's happening at the anode here. So if you look carefully, what my products are, I'm going to get water being produced and oxygen gas is being produced here, right? That's what's going to be produced at the anode. In the case of the cathode now, right, the cathode is my negative electrode. But when you look here, you realize, wait, all I really have here is H plus. So this is going to be this, 2H plus aqueous, right, plus 2 electrons produces H2 gas. Now, what CXC is giving you marks for here is to write the proper half equation, and what they give you marks for are the state symbols. So please don't give them the answer and just forget to put the state symbols. You need to put any state symbols here. right? So this is the first electrolysis you guys need to know, the electrolysis of dilute sulfuric acid, right? And please, you need to know these equations. In the exam, watch what's going to happen. If they were to give you this in the exam, they will give you 3 marks for this, right? Just to write this equation, and they would also give you 3 marks for this. So be prepared to answer questions like this. You can't afford to lose 6 marks in the exam, right? So you need to learn these equations. Now, the next electrolysis that we need to be aware of, right? The next one we need to know, we need to look at concentrated sodium chloride, right? Concentrated sodium chloride. So before you can analyze what's going to happen here, you should write down what ions are present. So if you have sodium chloride present, right, the ions that I have present will be Na plus, right, because you have sodium chloride. And this here is going to be Cl minus, the chloride ion. Now, again, once you have a solution, water is always present. Even though you're seeing concentrated there, water is always present. So you have H plus ions from the water, and you also have OH minus ions from the water. Now, what you have to do now, you have to figure out here what ions are going to be discharged at the anode. Now, your anode, like we said, it's your positive electrode. Again, the ions that are going to migrate towards the positive electrode will be these 2 ions, the chloride and the hydroxide. But then you have to make a decision. Here what is actually going to be discharged here? Now, if you go to the table, you realize, wait a minute, look at where chloride ion is and look at where OH minus ions is. So the first thing that's going to pop into our head, you might say, here OH minus has to be discharged. But the thing is, you see this word here, concentrated? This affects what is going to be discharged. Remember at the beginning I said we have 3 factors that affect what is discharged. Concentration was one of them, right? So therefore, because it's concentrated sodium chloride, right, your chloride ions are going to be discharged. So it's Cl minus, so it's going to be 2 Cl minus aqueous, right, produces 2 Cl2 gas, right, plus 2 electrons, right? That's what's going to happen here. So it's 2 Cl minus produces Cl2 gas plus 2 electrons, right? That's all. I made a mistake here. This should be just Cl2, right? So it's 2 Cl minus produces Cl2 plus 2 electrons, right? Now at the cathode now, again you have a decision to make. Your cathode is your negative electrode. But if you look carefully, you have 2 sets of cations here. You have sodium ions and you have hydrogen ions. So which one is going to be discharged? Again, if you go back to your electrochemical series, you have sodium and hydrogen. Look at where sodium is. Look at where hydrogen is. That means that hydrogen is going to be discharged in preference to the sodium, right? So sodium is not going to be discharged at all. So in this case here, hydrogen is going to be discharged. So it's going to be H plus, so it's 2H plus aqueous, right, plus 2 electrons, right, produces H2 gas, right? That's what's happening here. So again, if this were given to you in the exam, you're getting 3 marks for this, and you're getting 3 marks for this, right? So what CXC is looking for is the correct equation, it has to be balanced, and it also must have state symbols. So if you don't have these state symbols, you're going to lose marks. So be aware of that. So that's my second one. That's concentrated aqueous sodium chloride, right? So it's normal common salt that you have in the kitchen. You take some salt and you mix it in water and we perform electrolysis on it. This is what's going to happen. You're going to have chlorine gas being evolved and you're going to have hydrogen gas being evolved, right? Now let's make a slight adjustment now. We're going to do electrolysis again on sodium chloride, but what we're going to do now, we're going to use dilute aqueous sodium chloride. That's the change that we're making, right? So again, we have sodium chloride, so it's NaCl. So my ions present here is going to be Na plus and Cl minus. Again, we're going to have water present, and from the water you're going to get H plus ions and OH minus ions, right? That's what we're going to get. Now your anode, like we said, it's your positive electrode. So therefore, these ions here, the chloride and the hydroxide, going to migrate towards the anode. But notice we use dilute aqueous sodium chloride. We didn't use concentrated this time. So what we're going to do, based on our position in the electrochemical series, this here is going to be discharged in preference to the chloride ion. So OH minus is going to be discharged. So we just learned out that formula here. That's going to be 4 OH minus aqueous produces 2 H2O liquid, right, plus O2 gas plus 4 electrons. So I'm going to repeat this again. You all need to learn off this equation. This equation, you're going to meet it a lot of times. Need to learn this off, right? So that's what's going to happen at the anode, right? The OH minus is going to be discharged in this particular instance. Now here's the part that students make mistakes with, right? So when it comes to the cathode now, your cathode is your negative electrode. But when you look at the negative electrode, we have two options. Either Na plus or H plus could be discharged. Now, the only way to determine which one is going to be discharged here, we must look at the electrochemical series. Again, we're looking at hydrogen here and we're looking at sodium. The fact that hydrogen is below sodium, it means that hydrogen is going to be discharged. So I see some students telling me, well, sodium should be discharged. That's not true, right? So again, you're going to put 2 H plus aqueous, right, plus 2 electrons produces H2 gas, right? That's what's going to happen here, right? So this is what I'm getting at my cathode. So you guys, again, you need to know your equations, and I'm going to keep putting this until you remember. You're getting something like 3 marks, right? So don't go next month here and write the exam and lose those 6 marks, right? Make sure you know how to write these half equations. That is what CXC loves to bring, right? So make sure you all understand this, right? Right, so this is concentrated and dilute. That's what CXC wants you to know. The next electrolysis that you need to be familiar with is this one here, right? Where we're using aqueous copper 2 sulfate. Now this one is an interesting one, right? And this has to do with the fact that depending on what electrode I use is going to affect what is going to happen, right? So here's what's happening here. Let's get back my red pen. My electrolyte is aqueous copper 2 sulfate. So if it's copper 2 sulfate, that's CuSO4. So the ions present here will be Cu 2 plus and SO4 2 minus, right? That's what's happening here. But again, because you're in solution, you have water present. So I have 2 sets of ions present, H plus and we have OH minus. That's what we have here, right? Now, let's see what's going to happen at the anode. So my anode is my positive electrode, my cathode is my negative electrode, right? So we need to be able to predict what is going to happen in this particular scenario, right? Right, so we already know what ions are present, right? So then at the anode, these are my 2 ions that are going to migrate towards the anode. You have the sulfate ion and the OH minus ion. But if I go back to my electrochemical series, look at where OH minus is and look at where sulfate is. Sulfate is quite up here, right? So therefore OH minus ion will be discharged in preference to the sulfate. So what's going to happen here is going to be the same equation we learned of before, right? Which is 4 OH minus aqueous, right? Produces 2 H2O liquid, right? Plus O2 gas, right? Plus 4 electrons. So that's what's going to happen here. That's what's happening at the anode, right? So this is how you're making decisions based on position in the electrochemical series, also based on concentration, also based on whether my electrodes are inert or active, right? In this particular case, we're using graphite electrodes. So this is what's going to happen at the anode, right? at the cathode now, the cathode is my negative electrode. But look at what's happening here. You have Cu2 plus and H plus. Again, go back to your electrochemical series. Look at where H plus is and look at where Cu2 plus is. Because copper is below hydrogen in electrochemical series, copper is going to be discharged in preference to the hydrogen. So hydrogen is not going to come out in this case here. So what's happening here is copper is going to be discharged. So Cu2 plus aqueous, right, plus 2 electrons produces Cu solid. So copper ions are going to be discharged at my cathode. Now look at where your cathode is. Your cathode is this terminal here, right? This one here. This is my cathode here. Now what's going to happen here, in solution, your copper ions are going to be deposited here. So Cu2 plus, right, ions are going to be deposited on the cathode. So what's going to happen is that the cathode is going to be coated with copper, guys, right? So the cathode here is going to start to get coated with copper, right? So sometimes it asks you about, especially copper sulfate. And something you need to know about copper sulfate. Copper sulfate is a blue solution, right? So if you ever worked with copper sulfate in a lab, copper 2 sulfate is a blue solution. So CXC sometimes asks you, what are some observations for this particular electrolysis? So your first observation is that copper is going to be deposited. So your cathode begins to be coated with something that my CXC calls it a pinkish solid. If you see pinkish solid, that's copper, right? So your cathode is going to be coated with copper. Another observation is that the reason why this solution is blue, right? The reason why this solution is blue is because of Cu2 plus ions. But if your Cu2 plus ions are being discharged, meaning that they're coming out of the solution and being converted into solid copper, it means that the amount of copper inside here is going to decrease. The copper ions decreasing, therefore the color of the solution is going to fade, right? That's an exam question that you need to know the answer to. The blue solution, right? So let's say you had a blue solution here. What's going to happen over time is that blue solution is going to fade. It will eventually become paler until it becomes colorless, until all the copper has been discharged, right? So these are two observations that you need to be aware of. CXC can ask you that. Right? So make sure you know your observations. So one, blue color fades, right? Well, you can say copper deposited. So copper deposited at my cathode. Right? The second thing is that the blue color fades. Right? So these are observations you need to be aware of. They can ask you that in the exam. Now, we're going to do the electrolysis of copper sulfate again, but we're going to make a change, right? This time, what we're going to do, we're going to put an active electrode this time. So instead of using graphite, because graphite is what we call an inert electrode, we're going to use copper this time. So we're going to use a copper anode, and we're going to use a graphite. We're keeping a graphite cathode here. But what we've done, we've changed the anode. The anode is now made of copper. Now, again, your first step to analyze this, you need to look at what is present. Your electrolyte is aqueous copper 2 sulfate. So this is CuSO4. That's copper 2 sulfate. So the ions present will be Cu2 plus and SO4 2 minus. Those are my two ions present. Then we have water is always going to be present here. So what's happening here is that you have H plus and you have OH minus. Those are my ions present. Now, at the anode now, remember your anode is your positive electrode, right? So what's going to drift towards your positive electrode will be these guys here, right? So you have sulfate and you have OH minus, right? Sulfate and OH minus. Now, in this particular case here, what's going to happen is that you have, one second. Right, so your anode is your positive electrode, right? Now, your OH minus and your SO42 minus, they would want to migrate towards the anode. Now, your anode here is made up of copper. But the funny part in this particular electrolysis, because copper is what we call an active electrode, none of these guys here are going to be discharged. You're not going to discharge sulfate. You're not going to discharge OH minus. What's going to happen is you see that copper anode is going to go into solution. So what's happening here is you have Cu solid, right, is going to produce Cu2 plus aqueous, right, plus 2 electrons. That's what's going to happen, right? Cu2 plus is going to be produced here. Now, at the cathode now, remember your cathode is your negative electrode, right? So at your cathode, you have your negative electrode. What's going to happen here is that you have H plus and you have Cu2 plus, that's these two ions, they're going to migrate towards the cathode. But again, just like in the previous electrolysis, what's going to happen is that Cu2 plus is going to be discharged. So Cu2 plus aqueous plus 2 electrons, and that's going to produce Cu solid. So what's going to happen here is that Cu2 plus ions coming out of solution and it's going to start to coat the cathode, right? Just like in the previous electrolysis we did. So copper is going to be deposited here, right? So Cu2 plus is coming out of solution, but at the same time, you see this anode here, this copper anode, this is going into solution. So at the same time, Cu2 plus coming out of solution, Cu2 plus is also going back into solution. So my observations are, those are exam questions that they ask you. The blue color remains the same because you're pulling copper ions out of solution, but at the same time, you're putting it back. So therefore, the blue solution remains the same. So blue color remains the same. Right? That's what's going to happen here. The blue color remains the same. Now, the second observation, we already know that copper, right, that pinkish solid is going to be deposited at the cathode. So copper deposited at my cathode. Now, there's a third observation here that's going to take place. You see the anode, because the anode is an active anode, it's made up of copper, the mass of the anode is going to decrease. So mass of anode decreases, right? Because the copper is going into solution, right? I'm hoping you guys follow that. So while you all deciding if you understand that or not, right? If you haven't done so as yet, please hit like and subscribe to my channel, right? And just a reminder, I do give online maths, admaths, physics, and chemistry classes, right? You can send me a WhatsApp at this number here, right? Existing Form 5 students, all my Form 5 classes have currently ended, right? So I'm taking new students from August, right? Right, so I've seen a lot of you all saying yes. Great job, guys. Glad you all following. Right, now let's move on now. So those are the electrolysis that CXC says, here what? We need to learn this. Right, so I've done exactly what CXC wants you all to know. Right, now there's another electrolysis we need to be familiar with. Right, and that's this one. So here's what's happening here. you need to understand when we do electrolysis on something called lead bromide, right? Lead bromide. So I'm just completing the circuit here, right? So this is my positive terminal, negative terminal, right? And we are performing electrolysis on, look at what we're doing it on, molten lead bromide. Now, you all need to understand that a solid ionic compound does not conduct electricity, right? If you have, let's say, common salt in the kitchen as sodium chloride, if you try to pass a current through sodium chloride, nothing will happen. It will not conduct. There are only two ways you can make sodium chloride conduct, and that is to either dissolve it in water to make the ions free and mobile, or if we take the sodium chloride and we melt it, we just apply enough heat so that the sodium chloride turns into a liquid, right? So your syllabus says you need to be able to perform electrolysis on what they call a fused halide. So the example we always use would be lead bromide, and the formula for that is PbBr2. That's lead bromide, right? So in order to perform electrolysis on this, it must be heated. If you remove the heat, then that's it. Electrolysis cannot take place. So you need to heat the lead bromide until it turns into a liquid. Only then will the ions become mobile for electricity, conduction of electricity to take place, right? So again, you have, so this here is my anode, right? This here is my negative electrode, and that's called my cathode, right? That's my negative electrode. So this here is positive and this here is negative, right? Now, first things first, we need to figure out what ions are present. So your formula is PbBr2, right? That's the formula for lead bromide. So therefore, the ions present here will be Pb2+, right? And then we will also have the bromide ion, which is Br-. So those are my ions present. Do not come and say we have water present. Water is not present here because what you've done is taken the lead bromide and you've heated it sufficiently so that it melts, right? So there's no water present here. In this particular one, notice what I have here, molten lead bromide. So I haven't added any water at all. So I only have two ions present. So let's do it like this. So at the anode, right, which is my positive electrode, right? At the anode, the ion that's going to move towards that will be the Br-. So my equation is going to be 2 Br- aqueous. Sorry, I put in aqueous there, but it's really liquid, right? It's liquid. It's not aqueous because we haven't added water. It's liquid, right? Produces Br2, right? In this case here, you're going to get liquid, or you could put gas, right? Plus 2 electrons, right? So either you put Br2 liquid or you put Br2 gas, that's fine, right? So that's what happened at the anode. So you see they say a brown gas, that brown gas there is really bromine vapor that you get in there. So bromine, right? Bromine is actually a liquid, right? But what's going to happen there, it's going to warm up and bromine gas or bromine vapor is going to be produced. So this here is bromine. Right, bromine vapor. That's what you're going to get here. Now at the cathode right, which is your negative electrode, the only ion you have left now is this Pb2+. So what's going to happen here is Pb2+, again you're going to put liquid, not aqueous, plus 2 electrons, right? And that's going to produce Pb solid, right? So you see this silvery metal that they say here? That silvery metal here is lead. That's what you're going to be producing here, right? So you need to be familiar with this diagram, right? In this particular case, you are heating your electrolyte until it melts, right? For this particular one here, my electrodes here, this particular one here, this is graphite. I'm using graphite electrodes in this particular one here. Right, so we're using graphite electrodes for boot. Right, we're using graphite electrodes for boot. Right, so this is electrolysis of what we call a molten halide. Right, So this takes care of the electrolysis that we need to be aware of, right? What I'm going to look at here with you guys is how do we do our electrolysis calculations, right? Because this could potentially come as a question in your exam. Now, here's what's happening here. So we have something called the Faraday, right? That's a unit that we use when it comes to electrolysis calculations. So it's called the Faraday, and 1 Faraday is equal to this, 96,500 coulombs. Now, for those of you who don't do physics, right? Basically, whenever you have charged particles flowing in a circuit, charged particles or charge is measured in something called coulombs. And there is a unit called the Faraday. 1 Faraday is equal to 96,500 coulombs, right? Now, apart from that, there's one formula that you all need to know, which is this. Q is equal to I multiplied by T, right? Just remember, quit. Q is equal to IT. Q, in this case here, is my charge. So this here is charge in coulombs, capital C. This here is my current. So for those of you not doing physics, current is measured in amperes. So that has to be in amperes. And this here, my time, right, that needs to be in seconds. So whatever time they give you in the exam, you need to convert that time into seconds before I can use the formula, right? Now let me show you how you're going to use this. Let's talk about copper. Let's say you have Cu2 plus, right, aqueous, plus 2 electrons produces copper solid. Let's say you have this half equation here. That half equation tells me something, right? That half equation tells me something. You see this 2 in front of the electrons here? That tells me that 2 moles of electrons, right, produces 1 mole copper. I can tell that from that equation. 2 moles of electrons. Look, there's a 2 in front of this here. So that's 2 moles. You're not seeing a 1 in front of this copper, but we know there's a 1 there. We don't normally write it, but it's there. So 2 moles of electrons produces 1 mole of copper. Now the thing is, 2 moles of electrons, right, is actually 2 Faradays. So therefore we can also say that 2 Faradays, right, produces 1 mole of copper. We can also say that, right? We can even convert this Faradays into coulombs. So we can say 2, if it's 2 Faradays, it'll be 2 by 96,500 coulombs produces 1 mole copper. All of that I can tell from this equation. Right? Now, another thing you can write from this equation here, let's say you know the relative atomic mass. So the relative atomic mass, right, or the mass number of copper, right? So the mass number of copper is actually equal to 63.5, right? Now that I can use this also to write another statement. So I can say 2 by 96,500 coulombs produces, and instead of using moles on the right hand side, I can change this 1 mole and put it as grams. So I can say produces 63.5 grams of copper, right? All of that information here I can tell from this equation, right? And that is how we analyze half equations in order to work out whatever CXC wants us to work out, right? So I have 2 examples for you all to look at here. So let's do that. So here's what's going on here. So a current, right, of 5 amps. So I know what my current is. So this here is my I. That's my current. It flows through an electrolyte of molten lead to bromide. You all know what lead 2 bromide is. We just looked at it there. So PbBr2, that's lead 2 bromide. For a period of 1 hour, calculate the mass of lead deposited at the cathode. Now, before you can even do any electrolysis calculation, you must write the half equation, right? You had PbR2, so therefore the ions present here would have been Pb, 2 plus, and Br minus. Those are my ions present, right? So we're talking about the cathode here, right? So the ion that's going to move towards the cathode here, right, is going to be my lead, my Pb2 plus, right? Because your cathode is your negative electrode. So the half equation that we're looking at here in this instance is going to be Pb2 plus, right? Remember, this is liquid, right? Plus 2 electrons produces Pb solid. So that's my half equation. Before I can do any calculation, I need to have the half equation. Now, they are giving us a piece of information here. They told us the current and they told us the time. So what we need to do, we need to work out the actual charge. So if you don't know how to even work out the question, guys, please write down this formula. Q is equal to IT. My current here is 5 amps multiplied by my time. Now here's the thing, guys. There's a little trick here. The time here is given in hours. So you need to convert that hours into seconds. 1 hour is 60 minutes. And in every minute, you have 60 seconds. So 1 hour is actually 60 multiplied by 60. Right? So 1 hour is actually 60 multiplied by 60. So you all need to be familiar with that. Now, let's do a little calculation here now. So what I'm going to do, I'm going to work out the charge that actually flowed in the circuit. So that is 5 multiplied by 60 multiplied by another 60. So what I did there, I converted into minutes, and then I converted minutes into seconds. So this is going to give me 18,000 coulombs. That's the charge that flowed during that time interval. 18,000 seconds. 18,000 coulombs. So let's do that. Let's put that. So this is 18,000. So if you all don't know how to work out anything, please work this out first. Right? Work out the charge that actually flowed in the circuit. Right? You'll get some marks for that. Now, what else do we need to do? Right, so we know the charge. Now, we need to use the equation here to write a statement. Now, you want to figure out the mass of lead being deposited, right? We need to find the mass of lead, right? Now, can't remember the relative atomic mass of lead offhand. So give me a sec here. Right, so lead is 207, right? 207. So the relative atomic mass of lead is equal to 207, right? Not 209, 207, right? So CXC needs to give us this in the question, or if they give you a periodic table, you have to be able to find what is the relative atomic mass of lead. Now, according to this equation here, let's write the equation first. So we're looking at this. 2 moles of electrons produces 1 mole of lead. So write that. You're going to put 2 mole of electrons, right, produces 1 mole of lead, right? I got that just by looking at the equation. Now the thing is, we need to convert. On the left hand side, it's 2 moles. So we can say 2 Faradays, right, produces. And what we can do one time, since you know the mass of 1 mole of lead is this figure here, 207, I can convert this moles to grams one time. So 2 Faradays produces 207 grams of lead, right? So we get in there. We're not there at the final answer yet. Now, I can't work in Faradays. I need to work in coulombs. So remember, 1 Faraday is 96,500. So therefore, 2 Faradays will be 2 multiplied by 96,500 coulombs. Produces 207 grams of lead. Right? Now we are at the last stage now. Therefore, remember this figure here, this 18,000 is the actual charge that flowed in the circuit for 1 hour. That's the 5 amps flowing for 1 hour. That's 18,000 coulombs. So I need to work out for 18,000 coulombs produces, now here's what's going on here. We're going to cross multiply. I'm going to take this figure, this 18,000, multiply by 207, and then I'm going to divide by this figure here. So this is what we're doing. 18,000 multiplied by 207 divided by 2 multiplied by 96,500, right? And this here is going to give me my answer. Now let me show you how you're doing this in your calculator, because there are many students that have issues or they have problems working this out in a calculator, right? So let me show you what I'm doing. So first things first, right? So already I have the 18,000 in the calculator. I'm going to multiply by 207. I'm going to get an answer. This big number here. Divided by, now if you're doing all of this in your calculator, please use a bracket. You're using a bracket because in your denominator, you have 2 multiplied by 96,500. So this is 2 multiplied by 96500, right? Close my brackets here, equal. And what I'm going to get here is 19.3 grams, right? So my answer here is going to be 19.3 grams of lead. Right? So keep that in mind. Time must always be in seconds, guys. Right? If you don't do that conversion, then you're going to get a question wrong. All right, so that's my answer for that question. All right, now let's do our next calculation here. So in this one here, I have a current of 4 amps. So this is my I, right? It flows through an electrolyte. Look at what electrolyte is this time. Dilute aqueous sodium chloride for a period of 1 hour and 20 minutes, right? Calculate the volume of hydrogen gas produced at the cathode. And they also told us at RTP, right? So before, like I said, before you could do anything, you need to know which half equation you're going to use. So it's dilute aqueous sodium chloride. So let's just go back here. That is this one here. No, sorry. Is it this one? Right, is this one here. Dilute aqueous sodium chloride, right? Now we want to know what is happening at the cathode. Now at the cathode, look, this is my cathode reaction here. Hydrogen is going to be discharged. But let's just look at it, right? So it's dilute sodium chloride. So it's NaCl, right? And that's going to give you Na plus and Cl minus, right? But because it's a solution, you have H2O present. You're going to get H plus and you're going to get OH minus ions. Now, they want to know what is being produced at the cathode. Your cathode is your negative electrode. That's your negative electrode. So therefore, at the negative electrode, these two guys are going to migrate there. The sodium ions and the H plus ions. We already saw that sodium will never be discharged, right? So if you in the exam you find yourself putting sodium being discharged, that is wrong. You're going to get that wrong, right? It's hydrogen that's going to be discharged. So the half equation in this instant here is going to be 2H plus aqueous plus 2 electrons, right, produces H2 gas. Right? So that's my half equation that I'm going to be using to perform this calculation. Next thing, you need to know what charge flowed in the circuit. So it's Q is equal to I multiplied by T. So here's what I want you all to try to work out for me. Work out the charge for me. So I'll wait for you all to work out the charge for me, right? All right, so seeing some answers. Let's see which one is correct, because I'm seeing most of the answers looking the same. There are two answers that are slightly different. I can't say offhand which is correct, but let's work it out. So here's what we're going to do. You have 1 hour, but you also have 20 minutes, right? So here's what's happening here. Your current is going to be 4 amps, right? Multiplied by your time. Now you got to be careful with the time. The time is 1 hour and 20 minutes. So here's what you need to do. 1 hour, right, is actually 60 multiplied by 60. This is the 1 hour here in seconds, right? But we also have to add, you know what, let me work this out. Let's work this out up here. So my total time, let's work out the time by itself first. So that is 60 multiplied by 60, right? That is your time in seconds here. That's the 1 hour. Plus, we need to add the 20 minutes. So that 20 minutes is simply going to be 20 multiplied by 60. So this here is going to give me 60 by 60 is going to give me 3600. Plus 6 2s are 12, that's 1200. So therefore, this is going to give me 4800 seconds, right? That's going to give me 4800 seconds. You'll have to be careful with the time, right? So this here is going to be 4 multiplied by 4800. And let's see what I'm getting for that. So let's get back my calculator. So that's going to be 4 multiplied by 4800, right? And I'm going to get 19,200, right? That's what I'm getting there, 19,200. Right, so those of you who got that, that's correct, 19,200 coulombs. Right, so be careful. Be careful with those kinds of things, especially when they have minutes and hours in the same question. So what I did first, I worked out the time and then used that time here in my formula, right? So we know the amount of charge at fluid. Next thing we need to do, look at the equation. You have 2 moles producing 1 mole of hydrogen gas. Now, there are certain pieces of information that are required. So when we're talking about RTP, room temperature and pressure, right? 1 mole of a gas at RTP is 24 dm cube, right? 1 mole of a gas at RTP is 24 dm cube. So CXC has to give you this in the question, right? Now, according to the equation, we can say 2 moles of electrons right produces 1 mole of H2 gas, 1 mole of hydrogen gas, right? That's what's happening here. Now from here, now we can say we can't work in moles, right? We need to work in either Faradays or coulombs. So 2 moles, as I was saying, 2 Faradays, right, produces, right? Now we can change this mole here one time into dm cube, because the question asks us for volume of hydrogen gas. So I'm going to say 24 dm cube one time. So 2 Faradays produces 24 dm cube of H2 gas, right? So we're getting there. We're not there yet, but we're getting there. Now I need to convert this Faradays into coulombs. So this is going to be 2 by 96,500 coulombs produces 24 dm cube of H2 gas. Right, that's what's happening here. Now, what we're going to do now, we're going to take the answer that we got previously, which is this, the 19,200, because that's the actual time, right? Sorry, the actual charge at flow through the circuit. So we're going to say 19,200 coulombs produces, right? And what we're going to do here, we're going to cross multiply. So you're going to take the 19,200 multiplied by 24, and I'm going to divide that by 2 by 96,500, right? And that's going to give me, let's work that out. So let's get back the calculator here and let's do this again. So it's 19,200, I already have it in the calculator, multiplied by 24, right? Then I'm going to divide that by 2 by 96,500. Close the brackets, equal, and I'm going to get 2.39. So I'm going to get 2.39 dm cube of H2 gas. Yeah, Keon, you can work in cm cube if you want, right? You can work in cm cube if you want, right? So what Keon is saying is this. Now, 1 dm cube of a gas, right, is actually equal to 1000 cm cube, right? So sometimes you may have to work in either dm cube or centimeter cube, right? So all you have to do if you want this answer in cm cube, just multiply by 1000. That's it, right? That's it. Right? Now, there are two other applications that you need to know, and that is the purification of copper, right? So we use electrolysis in order to purify copper, and this is what the circuit looks like. You'll need to be able to sketch this, by the way. So this is my positive terminal, negative terminal. Right? So what we're trying to do, we're trying to get very pure copper, right? In order to do that, this is what happens. So you have, again, you need to have an electrolyte here. Your electrolyte in this case here is aqueous copper 2 sulfate, CuSO4, right? Aqueous copper 2 sulfate is my electrolyte. That's a blue solution. This here, your cathode, right, is a tin sheet of pure copper, right? That's a very thin sheet of pure copper. You see the anode here? This anode here is actually your impure copper. So this here is impure copper, right? Now what's going to happen here is that the copper from, let's use a different color here. The copper present in this impure copper here is going to do this. It's going to go into solution. And then from here, the Cu2 plus ions are going to go towards the cathode and it's going to form copper solid. So what's happening here is Cu2 plus is being added to the solution, and at the same time Cu2 plus is going to be deposited at the cathode, right? Now there's something I didn't draw inside here, but what happens at the bottom here is that impurities settle at the bottom. So this here is my impurities. Remember, the whole purpose of this here is to obtain pure copper. Right? That's what it is. It's to obtain pure copper, right? So this is how we purify copper. You all need to know applications of electrolysis, right? Now, there's one more electrolysis you all need to know about, right? And that's something called anodizing, right? So there's something called anodizing. This is the last one you need to know about. So there's something called, let me get my red pen. Now let's talk about anodizing first of all. So we have metals, they generally corrode, but let me show you what happens here. So if this metal here is iron, let's say this is Fe, right? Iron. When iron is exposed to water and air or oxygen, what happens is that the metal, right, the iron starts to corrode. And when it corrodes, it forms iron oxide around itself, right? And eventually it forms something called rust. Now, the word rust only applies to iron. With all other metals, we say they corrode, but rust, right? Iron, we say it actually rusts. So rust is actually hydrated iron trioxide. Now, here's what's happening here. When rust forms on iron, it flakes off the surface. So it flakes off the surface, right? If you all ever looked at a piece of metal, if you pass your hand on it, the flakes just fall off, right? And when the flakes fall off, it exposes more iron, and therefore more rusting is going to take place, right? However, the scenario is different when it comes to aluminium. So if this was, say, aluminium, now if aluminium is exposed to air, what's happening is that you form an oxide layer, right? And this oxide layer, it has a formula. It is aluminium oxide, Al2O3. So it forms an aluminium oxide layer. Now this oxide layer, right, it sticks to the surface, or it adheres to the surface, and what that does, it creates an impervious layer. It creates a barrier so oxygen and water cannot come in contact with the aluminium, right? So it helps aluminium when it oxidizes a little bit, right? If it oxidizes, it forms that aluminium oxide layer that prevents further corrosion, right? Now, there is a process that we use in order to increase the thickness of this oxide layer. And increasing the thickness of this oxide layer is called anodizing. And it's an electrochemical process again, right? So here's what's happening here. We have a circuit, right? And let's say, so in some of your homes, you might see an aluminum door frame, right? So let's say you have an aluminum door frame, right? So some of you all may have this in your house. That's an aluminum door frame, right? And we just have an electrode here, right? And you want to anodize this aluminum door frame, right? All you need to do is to perform electrolysis, right? But what we're using here, we're using a cathode, right? The cathode here is going to be an inert electrode. So what we're going to do is use, so my electrolyte, sorry, is dilute H2SO4. That's what we're using as my electrolyte, dilute H2SO4. This here is, let's say, graphite, right? And this here is my aluminum door frame. So aluminum door frame, right? That's what that is. So this is my positive electrode and my negative electrode, and that's my aluminum door frame. So when you perform electrolysis here, this is what's happening at the anode. So at the anode, right, what's going to happen here is that because it's dilute sulfuric acid, right? So we did this before. What's going to happen here is that OH minus is going to be discharged. So for OH minus, aqueous produces 2H2O liquid plus O2 gas plus 4 electrons. Please, again, learn of this equation. You need to know this, right? Now, what is actually anodizing for us? You see this here? Oxygen gas is being produced. That oxygen gas, bubbles of oxygen gas producing all here, all around the aluminum. And what that is doing is actually increasing the thickness of the oxide layer on the aluminum door frame, right? So this process here is what we call anodizing. It's how we increase the thickness of my oxide layer, right? Right? And so guys, this brings me to the end of electrolysis, right? This brings me to the end of electrolysis. This is what you guys need to know for the exam, right? So this is all the time that I have today. So I hope that this session was productive for everyone, right? So like I said, if you haven't subscribed to my channel, please hit subscribe, hit like, right? You can share the videos if you want, that's fine, right? Again, I do give online classes, and my new classes start in August. All right. So guys, that's it for me. I hope you all enjoy the session.